Alright, let us now take a look at that expression. So we need to maximize over the alphas, and that expression here basically will give you the alphas. Yeah? I'm not going to do this here, it's not necessary, but there's a few interesting things you need to see. Well, first of all, here, that means that maximizing your Lagrangian with respect to alphas only depends on dot product of the samples. Yeah, that's quite an interesting thing to notice. Now there's a few other things. Look at this expression here. We have alpha I times yi and then times w transpose x plus b minus 1. Yeah. And we know that this expression here is 0 in the gutter. Yeah, we said it a few minutes ago. 0 in gutter. This is the gutter between the red lines. So, if we multiply with alpha, so if the vector is in the gutter, that means that your alpha I is positive. Yeah, because the 0 here is because of this one. Yeah. Now the alphas that are positive, the vectors associated with that, these are the support vectors. Yeah, support vectors are the vectors where alpha I is positive. Now let's take a look at what it basically means. So we have the two classes here. We have three support vectors. Yeah, here are three, the ones that I circled. So three support vectors. Yeah. So even if you have a sum over, your sample size, the only points that are going to contribute to your L of alpha maximization are going to be these 3 points. All the other points, your alpha will be 0 and they will not contribute. Yeah? So that method is very robust to outliers. If I put a 0 here and a minus here, it doesn't matter. They will not contribute. Only points in the gutter, or that support the gutter, better said, will contribute. Now, if we look at the W here, we have W equals the sum over alpha I, yi, xi. Yeah. But we can make this calculation very easy because alpha I is 0 for all the points except the support vectors. So this sum is for xi support vectors. Yeah. So in this case is 3 we have, yeah. So we don't have to go and calculate it for all the samples.